Hello everyone. Today's lectures we have discussed the topic organic spectroscopy. In these topics, now we are going to discuss some terms that is shifting absorption of bands. These bands can show due to change in the structures of the molecules, the positions as well as height of an absorption band. They will change. But you know that the chromophore and chromophore oxochrome interactions increases, and then length of the conjugation and hence decrease the energy required of the transition. It means that the chromophore and oxochrome interaction increases, then increase the wavelength with conjugations and decrease the energy. So these terms now we are going to discuss as like first terms hyperchromic shift. Such shift means that the intensity of radiations, the shift can accompany by increase the intensity of the radiation, right? This hyperchromic shift, this arrow, this vertical position increase the intensity of absorption of radiations. This is called as hyperchromic shift. Next definition or next terms we have see that bathochromic shift. It means that the absorption band shifted to a longer wavelength. Absorption bands are shifted to a longer wavelength like this to increase the wavelength. So the absorption band shifted to a longer wavelength. This is called as bathochromic shift. Right? Next terms now we have see hypochromic shift. It means that decrease the intensity of absorption of the radiations is called as hypochromic shift. See this arrow, it means decrease the intensity of radiation, right? Decrease the intensity of radiations or reduce the intensity of radiation is called as hypochromic shift. And next is a hypsochromic shift. Hypsochromic shift, it means that the absorption takes place by decrease the wavelength of the radiations, which is called as, right, decrease left hand side, it means decrease the wavelength, right hand side increase the wavelength. It means you decrease the wavelength for the radiations is called as hypsochromic shift, or it is a shorter wavelength. It means decrease the wavelength is called as a hypsochromic shift. Now we have see some definitions for those as like firstly, here the absorption band shifted to a longer wavelength is called bathochromic shift, and the absorption takes place by increase the intensity of radiation is called hyperchromic shift, and absorption band shifted to a shorter wavelength is called hypsochromic shift, and absorption takes place by decrease the intensity of radiation is called hypochromic shift. Now such terms we have seen some examples for given those shift. So firstly we have seen this nitrobenzene can shows hypsochromic shift. It means that what is meant by hypsochromic shift? Absorption band shows shifted to a shorter wavelength is called hypsochromic shift. So nitrobenzene the value which is found to 270 nanometer, right? To 270 nanometers. But para dinitrobenzene, it shows 261 nanometers. From these nitrobenzene and para-dinitrobenzenes, we observe that decrease the value of the wavelength. It means shorter wavelength or decrease the wavelength of the radiation. Right? It is 270 nanometer. It is 261 nanometer. Why it is a decrease the wavelength? Because the chromophore oxochrome interactions, they will be more in these para-dinitrobenzenes. Why it is more? Because the two nitro group, they will increase or extend the conjugations, and the basic parts or base are used. Increase the conjugation, it means decrease the wavelength of the radiation by absorption. Right? Next examples now we have see are here, like the benzene. These benzenes are converted to the phenol, and phenol is converted to para-nitrophenol. But this benzene, now we have C here, there is no any functional group on this benzene thing. Therefore, it is a higher wavelength. It means it shows bathochromic shift, and if convert to phenol, it is decrease the wavelength, and after nitration of those phenols still decrease the wavelength of radiation. Right? So how will you observe this? From the values of, like this is shows 254 nanometer, it is 270 nanometers, and it is 354 nanometers. It is increase the wavelength or longer wavelength of the radiations. It means that it is 254 nanometers, it is 270 nanometer, and it is 354 nanometer. Why it is an increase? Because the extended conjugation, they will decrease, or chromophore oxochrome interactions will be decreased. Therefore, it shows para-nitrophenol, the value of this. But why it is a decrease? Because this nitro group act as electron withdrawing group, and these are electron donating group. So you see the electron donating group can decrease the extended conjugation for or destabilize these electron withdrawing nitro groups. Okay, so decrease the conjugation. So UV radiations can absorb by the molecules, and they change the electronic levels of the molecules, and therefore the very large energy changes as compared to rotational and vibrational energy changes. The change in the wavelength, the change in the electromagnetic spectrum or the electronic levels, which is accompanied by the change vibrational as well as rotational energy levels, and therefore the wavelength absorbed in the energy levels changes are very close to each other, and therefore absorption band overlaps with each other and producing broad bands in UV spectrum. The last times or many times asked why UV spectrum are shown broad. Why it is broad? Because the wavelength absorbed energy level changes are very close to each other, and therefore absorption bands can overlap each other to produce broad spectrum or broad bands in UV spectrum. Now, some examples can show different values of number of functional group. So, firstly, we have the alkanes. In alkanes, the last times also we have see. So, which types of the bonds which is present in alkanes? Mostly the sigma to sigma star. Sigma bonds present mostly in alkanes, and therefore sigma to sigma star transitions can occur in the region is about 140 to 150 nanometer wavelength absorbed by those radiations of the alkanes. But when these radiation can coupled with oxochrome due to N2 sigma star transitions, then the compounds like the carbonyl compounds which produce such a transitions like the pi to pi star transitions as well as N2 pi star transitions. N2 pi star transitions which is observed due to the lone pair of oxygens and the carbon oxygen double bond, that is pi bonds. Therefore, N2 pi star transitions are observed in carbonyl compounds as well as pi to pi star transitions are observed. So, various carbonyl compounds and their values are shown here, like aldehyde, it is 180 nanometers due to pi to pi star transitions and 290 to 295 nanometers due to the N2 pi star transitions are observed in aldehyde. Nextly, ketones. The ketones, the value is 190 nanometer found is due to pi to pi star transitions, and 270 to 280 nanometer is found due to N2 pi star transitions in ketones. Similarly, one more examples like saturated monocarboxylic acids. The saturated monocarboxylic acids was found to 200 to 210 nanometers due to it is present the N2 pi star transitions. And in ester they shows it about 200 to 220 nanometers, and amide they will show 205 to 220 nanometers due to N2 pi star transitions which is observed in esters as well as amides. So for those values which shows which type of the transitions can observe on these different carbonyl compounds. Nextly, then we have the alkenes like the carbon-carbon double bonds, and these carbon-carbon double bonds which is conjugations, then they will show different values. For example, when ethylenic double bonds are conjugated with carbonyl group, then absorption can shift to longer wavelength. But at alpha beta unsaturated carbonyl compounds, they show two absorption bands, right? Conjugated carbonyl compounds, they will show the bathochromic shift, or it shows longer wavelength, and therefore this conjugated carbonyl compound shows two different bands. One band having the 220 to 250 nanometers, and strong bands which is 220 to 250 nanometers, and weak bands is about 215 to 330 nanometers. So these strong bands 220 and 250 nanometers, and weak bands they have 315 to 330 is observed due to the two functional group which is present as like carbon-carbon double bonds and carbon-oxygen double bonds. Similarly, these acid, ester and lactose also have absorption bands observed in the regions 205 nanometers and weak bands are 240 nanometers. For examples, now those molecules they will show these carbon-carbon double bonds which is conjugation with carbonyl carbon, right? So these carbonyl carbons are conjugated with this carbon-carbon double bond. Similarly, those carbon-carbon double bonds also conjugated with this carbonyl carbon. Similarly, crotonic acid also present the carbonyl carbon. They will have the conjugated with carbon-carbon double bonds. And they will show the different values like firstly, those molecules of protonaldehyde, they show lambda max values is about 218 nanometers and 320 nanometers. These values are shows like alpha beta unsaturated aldehydes. They have absorption bands in the regions is about these 218 to 320 nanometers due to the conjugated dienes. It shows higher the values, right? This is conjugated, sorry, dienes, not conjugated carbon-carbon double bonds, right? Carbon-carbon double bonds are conjugated with this. So extended conjugations with this carbonyl carbon, therefore value still increase, right? 218 nanometer to 320 nanometers. So two different values are found: strong bond and weak bands. But from these, how will you check this which is a weak band and which is a strong bands? Depend on their intensity of the radiation. So this is epsilon is max. Epsilon max means intensity of the radiation. So this 218 nanometers, it is a strong band and it is a weak band. Similarly, the mesetyl oxides also they shows two bands. One is 237 nanometers, other is 310 nanometers. The values of these found to be 237 is a strong bands and 310 nanometers is a weak bands for these carbonyl carbons is conjugated with these. Other crotonic acids, the values are found to be as like the lambda max is 206 nanometers and 240 nanometers, but extinction coefficient is about 13,500 for those bands, and therefore this is strong bands 206 nanometers and it is a weak bands due to less extinction coefficient. From these three examples, now we are compare then the values of lambda max, they will be increased, right? The values of lambda max, they will be increased. Now see here in alkane, the value is found as like simple aldehydes. The value is found to be 180 nanometers, 190 nanometers. But is aldehyde or the ketones conjugation, it will shows increase 180 nanometers simple aldehydes, but it is value is still increase are here like 218 nanometers. Mesetyl oxides also increase the value 237 nanometers, but at simple ketones the value is about 200. It is also increase the value of acids like 206 nanometers, right? So from these three examples, we observe that if increase the conjugation, it means increase the value of lambda max. Now we have seen these other examples for the absorption of aliphatic dienes. They will show the values of wavelength is a shorter wavelength. Aliphatic dienes is about 270 to 228 nanometers. But those dienes, that is alicyclic dienes, for example 1,3-butadiene, that has lambda max value is 270 nanometers and intensity is 21,000. Whereas cyclohexa 1,3-diene still increase the value is about 257 nanometers, right? It is a 1,3-butadiene, right? This is a 1,3-butadiene. The value is 270 nanometers. But in cyclohexane 1,3-butadiene, the value still increase 257 nanometers, having the intensity is 8,000. Why it is observed? Then we compare these two, that is 1,3-butadiene and cyclohexane 1,3-dienes. It is increase the conjugation. How will you increase? This cyclic ring, it is a one conjugation. The cyclic ring we consider as one conjugation. This is a carbon-carbon double bonds. It is also two conjugation. But it is not here cyclic, that is a extra conjugation or extended conjugation are here. No presence, therefore the value is less at 270 nanometers. And it is a 257 nanometer will increase due to extended conjugation due to one cyclic ring. Next examples we have see like in heteroannular diene. Heteroannular dienes and conjugated dienes which are different. It means that the heteroannular dienes, it means the two carbon-carbon double bonds, it is not symmetric. But in homoannular dienes, the carbon-carbon double bond which are conjugation, they are symmetric. But in conjugated double bond are not same in the ring. It means that one of the carbon-carbon double bonds it is in a ring and one carbon-carbon double bond is out of the ring. Such a system which is called as heteroannular diene. Both carbon-carbon double bond present in a ring, it is called as a homoannular diene. Right. So both conjugated double bond in the same ring, generally the value of homoannular diene it is higher than heteroannular diene. The homoannular dienes, the value of lambda max is 256 to 265 nanometers, having the extinction coefficient 2500 to 1000. And then this heteroannular diene, the value is still decreased, that is 230 to 240 nanometers. But it is an increase, extended conjugation for the one cyclic ring, it is in a conjugation, because this carbon-carbon double bonds in the ring, they are conjugated with each other. So extended conjugations will affect the value of lambda max. But in these examples, in a heteroannular dienes, one of the carbon-carbon double bond is not present in this cyclic ring, it is out of ring, or it is a heteroannular diene, the conjugate double bond, these double bonds is present out the ring, so it is not present extended conjugations as like this. Therefore value of heteroannular diene is still decreased, like a 256 it is 230, so 265 to 240 nanometers.